Okay.
Is that legal?
All right. I can't see here, so
Is that legal though?
I don't know if it's legal or not. So it's technically. Let me just pause this before I talk. Let's pause.
Yeah.
Okay, so let's continue. So what we're going to do from basically today, we are done with kind of like NLP part of the class, and then we're going to basically more focus on vision. And for the first part of the class, this works. We're going to start with latent variable models. And before we do that, just kind of like as like a refresher, you're going to see these slides almost every class moving forward. But we talked about one thing, that you always have some sort of data, and you need to represent this data in somehow. That's the problem Ashkan has right now. He wants to work on molecular data. He doesn't know how to represent it. That becomes challenging. So that's always the first thing. And coming up with a way to actually represent the data is not that straightforward. So you need to have some domain knowledge about that. And the next thing here is that, well, there are a series of model families that you want to basically use to be able to generate that data for you. Okay. And you also want a way to change basically compare these two together and see that how good is your model for generating in compared to the distribution of actual data. And what we will see is that as you tweaking these two pieces, as we talked about before, the types of generative models will change. Okay. And also it's important to basically decide that, well, what do you want to do with this model? Like, what's the end goal that you have? So you either basically try to do density estimation, or you have a goal like data generation. That means if I sample a new data point from this model that I created, it should look like a actual, for example, dog. Or if I pass in data of a dog to the model that I have, should give a high likelihood to that data point because it has seen that as a part of the training data. And there is a third scenario, and the third scenario is that, well, you want to do feature extraction. That means that you want to build these models. So later you could extract a feature and say that, hey, if I want to generate a dog, what should be the tail of a dog look like? You know, maybe that becomes like a feature extraction. You have always some sort of like one of these three tasks that is your goal when you do model generation. So one model that so far we have seen in from generating perspective, it was autoregressive, which in NLP we technically use just autoregressive because every next token generation becomes an autoregressive model, and the GPT models basically becomes one of this part of this family. And the way that we know in basically autoregressive model, for every token, that token or that basic data basically is depend on whatever comes before that, and they cannot see anything after. You know, that's the way it's. And we did that using some sort of like a masking, for example, to basically mask the future tokens. Now, when we are going to talk about basically the latent variable models, the first thing basically we want to focus here is that imagine this is like an image of celebrities. It's like there's a database, Celeb 10. And the first thing basically is that when you're looking at the images, there's all sorts of variabilities, like you have gender, eye color, hair color, and etc. Right? So the first thing is that, well, images, they have lots of variability in compared to, for example, what we have seen so far, like in text, you know, it's just the variability is not that much. And the other thing is that there are some factors that remains basically latent, that means hidden, because we don't know them specifically unless you basically annotate it. What's the factor? Like when you're looking at the image, you just see an image. You don't have a basically feature that says eye color, for example, blue, or I don't know, hair color, or like, for example, brown, or so on. Those factors are part of the image, but they are not basically explicitly introduced as a data, unless you basically extract those information, which if you have lots of images, technically it's really hard to extract all those features by hand. So now the idea here is that those latent features, those basically features that we know are part of the image, but we don't have those, we are going to basically model them using something called latent variables, and we call that as used as Z as a latent variables. Now, so the way that latent variables, let's start on the left side. So basically, you have only seen this gray basically circle X. That's the data that you have. But in reality, we know that this data has some latent variables that we don't see. We just know it exists. So there's this relationship. Now, for example, if you look at this one image, you could assume that there is a latent variable gender, there is a ethnicity. Ethnicity then connects to eye color, hair color, pose, and so on. Similar like a base network, basically. You know, you have the nodes and you have parents, and this basically relationship exists. Now, the idea here is that this Z, these latent variables, they need to be chosen, okay, or learned technically. But it's important that if you selected Z's properly, that means if you do a good job at finding Z, then you can find this basically conditional X given Z. Because if I know the latents and I learned it really good, then I could answer a question, what's the chance this image, for example, is a person from this region given this basically latent features? Right? So you can basically answer something like that. Also, this P of X given Z could give you information that you can use for clustering, for example. You know, it's just because now you have this latent information. Then there is some challenges with this, and the challenge is that you can't manually create those, right? Because you know, maybe if your data is really small and that those latent dimensions are pretty small, yes, you can manually handcraft those. But in reality, is coming up with this relationship among latents, it's not going to be easy, and it's challenging. So now the idea here is that instead of we trying to come up with that relationship of and define those latent features, we're basically going to use some sort of like a neural networks to learn those latent features for us. Okay, so what you see here is, so let's say you have this basically Z, and this Z goes through some network and gives you the image that you have. Okay. Now here, what we are saying that, and what basically becomes the idea in industry was, or academy first, that Z latent variables, we want it to be something easy, something that it's not difficult to learn. Because if I'm trying to, so the way that you need to look at this problem is that why do we need Z actually? Let's first start with that. So you have an image, and sometimes you just want to do a classification. So you just need an image and you learn some features on it and you do classification. Sometimes you want to generate image. If I want to generate image similar to this, that means I need to learn features about this image. That means if I receive a prompt that give me an image about a dog eating a pie, your model should know what's a dog, what's a pie, and stuff like that in order basically to be able to generate, right? So that means you need to learn a series of basically latent features that you could sample from that latent features, pass it to a model and the model gives you an image. Okay. So that's why we need that latent, because we want to generate from that. The other thing could be like you have an image and this image is old or has a missing pixels and you want to regenerate it. In order to also do that, you need to have learned that some sort of like a latent representation over the topics or basically the types of image in order to be able to fill those missing pixels. So that's why we actually need those latent variables. Now, in what you see here, basically what we are saying is that when you want to present Z, the latent variables, present them as something easy. And the easiest thing here we can use here is a Gaussian with mean 0 and a standard deviation basically of I. Okay, so what does that mean? That means you're saying that okay, my Z basically is something like this, for example. We want it to be something easy to sample from. We don't want it to be a challenging distribution. So when you have that Z, so let's say let's on the surface what we are trying to do. So we try to generate image. We want to have a model that if I just start this model and I say, give me an image, it should be really a straightforward. And the straightforward here means that the step one is, there's a Gaussian distribution. You just randomly sample a point from this Gaussian distribution. That becomes your Z, your latent variables. Okay. Then you want to pick that Z, which is, is going to be a vector or however you present it, goes to a model, right? And that model is the neural network. And that neural network model is going to produce two things for you, basically. Mean and covariance. Okay, so there's a neural network that when it gets the Z as an input, produce a mean and a covariance. Now, when you have this mean and covariance, that goes to basically here. Then you want to answer this question. So imagine you are trying to create a pixel and you want to see what's the best pixel that I could put here. And you're basically answering this question. What's the probability of this pixel being, I don't know, like black, given I have this mean and I have this covariance? And given this basically, or we can first phrase it that this given Z, we know that in order to answer this question, you need to pass Z to a model. That model gives you a mean and a covariance. And that becomes a multivariate Gaussian. And in order to answer that, you need to sample from that multivariate Gaussian with the mean and the covariance. So this comes from a multivariate Gaussian with basically mean mu and covariance. So it technically has two steps. One step is that you have Z, which is itself is a straightforward, like a simple Gaussian. And then you have another basically Gaussian, multivariate Gaussian, which will basically be over the result generated by neural network. So there's one neural network here that gets Z, converts that Z to a mean vector and a covariance. Then you pass that mean and covariance to a Gaussian, and whatever you get over there is going to be the answer to this probability. Does that make sense? Yes.
Question. For example, in this example that we want to pick, so we want to generate a pixel. What is Z in this picture?
So Z, okay, that's a great question. So let's look at this problem differently first. So what we are basically saying that if you have one image, and this image has basically some characteristics in it. Like for example, here we see this image of this face of a lady. And basically what we are saying here is that in order to have this image in reality, this image has a series of characteristics. And those characteristics, like those latent characters, like a hidden characteristics that you could see, but the model doesn't know it explicitly, those could become the Z. Like for example, eye color, eyebrows, and stuff like that. Those are Z basically, because it's part of the image and you haven't explicitly basically framed those. Now the question here is that if I want to create image like this, how can I basically do that? And if your model just simply copy images, it just gives you the same image back and forth, right? Now, if you have series of images, if your model just copies, it becomes average across all of those. So you get a really like a Frankenstein basically image. So in order for your model to be able to generate actually an eyebrow, your model needs to understand what is an eyebrow, like how I can represent it. So that means your model needs to not just learn the data, learn what could map to that data. What could help to generate that data? That is the Z. That is the Z, this something that's latent, hidden, you don't know it. But what we know is that there could be some hidden representation that if I can learn that, I could generate images. Okay, does that so far make sense? Now, here what we are saying here is that for Z, this latent representation could be really complex, right? And in order for us to make this easy for learning, easier, not easy because it's not easy, let's enforce Z to be something straightforward, like a Gaussian distribution with mean 0 and like a variance of I, you know? Something that is easy to sample from, okay? So that is the idea here. It was like, okay, that means this latent, we know this is latent, but we enforce this latent to be a Gaussian. Now, the goal here will be that if you keep sampling from a Gaussian, the Gaussian is fixed. This is fixed in the learning, and as we will see, this part is a Gaussian, you've enforced it. The part that becomes the learning is this model, this neural network. This model needs to learn anytime if you sample a Gaussian to map that sample to that image. Okay, that's what we want to learn here. How to pick a latent, basically Z, something that's just a sample from a Gaussian. We have a model that processes this latent, come up with two variables, mu and covariance. Somehow, that if I put this mu and covariance into Gaussian, it tells me that what's the basically likelihood of this image, like increases the likelihood. So the better the model here in mapping the latent to mu and covariance, technically the higher that likelihood will be for an image. So that will be the goal. We want to increase the likelihood of, for any data, generating that data. If we can come up with this high likelihood for data from mapping from a latent to actual image, that means we have learned the latent features and how to map them to an image, basically. That's the end goal that we have here. Does that answer?
Yes, and one small thing. So we're picking, for example, for drawing an eyebrow. So it's like we're representing an eyebrow with a Gaussian distribution, and then
So we don't explicitly represent individual items. We sample one basically data point, and that data point is higher dimension, and we have a neural network that's going to map that. However, the model basically learned, and we will see there are different types of model that we're going to use for this mapping, to map it to a full image, not to just an eyebrow. So basically the Z that you sample is going to be a latent for the full picture. This model is going to be basically responsible for conversion of that. Now here, this mu and covariance, that means multivariate, what's the dimension of this? That's kind of like a hyperparameter you choose. But it depends. You could basically assume that, like, you look at image and you come up with, like, from domain expert knowledge, you basically say, I'm looking at the image and I pick 10 features to be important, like eyebrow, ears, and so on. So I enforce mu and covariance to be like a size 10. Or you just maybe don't do that explicitly, and you just, as a hyperparameter, you tune it and you decide on those. But it's not like that you do one sampling per dimension. Now you do one sampling for the image and you generate over that. Okay. Yes.
So for these kind of models, what is the training data? So like, what do we like feed the model while training, and for this kind of prediction, like how like we change that input to the model?
So your question is that what are we feeding to the model for training?
Yeah, and what do we feed it for prediction?
So if you think about from the autoencoder's perspective, so like this is just a general autoencoder. Autoencoders, they have X, the image, and they need to reproduce the same thing. Okay, so the autoencoders basically, they have an encoder, decoder. They encode the image. That means they break it down, you compress it, And then there is a different model that picks that compression, says that I pick this compression and I will reproduce the same thing for you. When you do this back and forth between encoder and decoder, it's kind of like a game of two basically algorithm together. It's kind of like they need to both progress at the same time, because encoders' job is to get really good as for encoding of the data. So at first it's really bad. It just does a really bad job. Decoder at the same time need to become really good from getting an result from encoder and recreating the data. So both of them basically they work together to be good at what they are doing. One of them job is to compress the data. The other one job is to decompress the data. This general autoencoder concept by default is not generative model. That means this cannot generate data for you. And I think we saw this in class 3 or 4, that if you want to convert an autoencoder to generative, the general autoencoder, not the variational, what you need to do is that mask it. And that's why we call it mask autoencoders, right? So what you could do in mask autoencoder is that you mask certain certain connections, and that by masking certain connection, you technically convert an autoencoder to a base net, because you enforce relationship between nodes to be like a parental relationship. In that scenario, your autoencoder could generate image. Otherwise, the default autoencoder cannot. Now, when it comes to latent models, which this autoencoder itself, it has a latent concept, and there's a vector in between here. That's a latent vector, but it's not generative. So in the scenario of the latent model for generation, what we basically do is a little different. So here, instead of, we will see better pictures of this, but technically when you have this data goes to a model, and this model basically it creates two vectors instead of one. One is mu, one is the covariance. Then you do a sample from this, you have a mu and covariance, you do a sample from a distribution like that, that gives you a vector, the latent vector. Then you pass that latent vector to a decoder, and that's supposed to regenerate the image for you. By doing something like this, the idea here is that, so in the general autoencoder, you just wanted this to become good as compressing, decompressing. Here, the compression is a bit different, because here you want to be really good at finding the distribution of the latent. Instead of just compressing it, you learn a distribution, a Gaussian, and that learning should be really good, that if you sample from this Gaussian, you could regenerate the image. That becomes basically the difference between this type of autoencoder and the general basically autoencoder. Okay, any question? You forgot it?
I thought it solved. I was thinking that we have the image. For example, for the first pixel, we know that it's black, so the probability of it to be black is 1. And then we use the simple Gaussian as the latent variable. And then the model gives us mu and sigma. We use mu and sigma to get probability from Gaussian distribution, and then we compare these two probabilities, and this gives us the loss.
Yeah. So
Is that correct, or?
No, let me rephrase something. Maybe I kind of misrepresent something here. There is a big difference between autoregressive models, which are sequential, we put the pixels, and autoencoders. So in autoencoders, they are one shot. So if you have 10 pixels missing, you don't do one at a time, you just get all 10. And then using that, you calculate what you basically say. So that means, let's say there are 10 pixels missing, and in one shot, you get those 10 pixels replaced. Then now you have a full picture, and this is what we will see today. Then you calculate the probability of this full picture. Based on that, you decide how good was this generation. Does that make sense? So, okay, so you have a picture that this part is all missing, right? And what you want to do is that you want to replace these tokens, like these pixels. And let's say there are all sort of combination basically you could put here, but what you do, you basically replace it with something. Overall, when you look at all your data, when you have a data set, our goal is always to maximize the likelihood of the data or log likelihood of the data, which is kind of something like if we have d data points, basically, you want to maximize the likelihood of every data point, basically. So this becomes every data point, and you have this hidden, latent, and then some model parameters. That's what you want to maximize this likelihood. Then this part itself, it has different definitions. Like this is a joint distribution. Joint distribution could be presented in technically two ways: conditional times prior, or likelihood times prior. And that likelihood times prior, you also could present it two different ways. One time x given z, one time z given x. So let's say you put x given z. So you have probability of xi given z and this times this. Okay. So the way that you decide if this image is good, is this generation is good, if this is maximized for all of the data points that you have, this multiplication. So this part is basically what's the likelihood of this image after you fill the values? How likely is this image? Imagine you have an image that's all missing in the sky, like the top part of the image is the sky, and you just filled all with black. Then if you ask this question, how likely is this image? It should be less likely because all of a sudden on top is everything is a different color, right? But if it's all blue, maybe it be more likely. So that basically will be the idea. And we haven't talked about that. We will go over those ones. But in autoregressive models, the difference here is that you do one at a time. And one of the things that we will see is that autoregressive models, as we talked, they are slow. Autoencoders, after training, for example, with these latent models, are fast because in one shot, they give you the whole generation. Okay?
So my question was about the training part, not the generation part. In training part, we have the image and we calculate the probability based on the mu and sigma that the model gives us. And that probability should be equal to 1 because we know what color is that pixel.
So that's actually for the training.
Yeah, for the training.
So you want to, this is basically all you need to do.
Maximum.
You try to maximize for whatever unknown parameters that you have, these models, these neural networks they have, you want to maximize this likelihood, right?
But we always use b equal to the Gaussian, the simple Gaussian, right?
So z is always picked from a Gaussian. The part that you would, as part of learning, in order to maximize the likelihood, what we have control over, or the model has, are those thetas and phi parameters. Part of the gradient of this, we try to find those somehow that maximize that for us. Does that answer that? Yes.
First thing is, what makes that z different from being a noise? Like, because it's just like, let's say in the first iteration that I'm trying to train that model, that learns the mu and that covariance. It's a sequence of numbers, right?
Yeah.
And then, but randomly, like previous time, if I change those numbers, it's coming from a Gaussian distribution. It's a little bit vague to me. And the second is what's the input to that model?
To which model?
The model that learns the mu and the covariance.
So z is the input to the model.
Yes, and what's the label that model learns and adjusts its weights to learn those?
What is the, okay, so there are a couple of questions. Let's go over this one at a time. What was the first one?
What makes z different from being a noisy?
So but actually that's a really valid question. So at first, Z is just a Gaussian noise. You just sample from that. And the idea is that you want to be able to map that to something. You want to basically, it's not about the Z technically, it's about the model that gets Z and maps it, right? One thing that we will see, diffusion models, actually they do something like that. They have an image, you keep adding random Z noise to it to the point that the image becomes all noise. It's not image anymore. Then you reverse engineering, you find a model that can denoise it to reconstruct the image for you, right? So that's what basically, for example, diffusion models, they focus on adding noise, and then denoising it. That's, we will see, that's why at the end, we will see that that's kind of like a more optimal way of generation, depending on also the, the task. Your second question was?
Model, what is that thing that we use it? Like what I mean is, you say it's image, okay, but it's difficult for me to picture it.
Image. The full image.
Isn't image, let's say, 784 vector?
Do a kill divergence between two images, right? Do some similarity between two images. You need to be able to compare those together, right? If you have two images and then you perturb, no, I mean like one input image, one you generate the image.
No, the input was Z.
No, okay. So I think let me rephrase it. So there are two pieces here. There's an encoder, there's a decoder, correct?
I missed the whole thing.
Encoder, the first part, gets the data, actual data, breaks it down. This is Z, latent, hidden. This is Z. Okay. Z goes to a decoder. So decoder is where you do generation. Encoder is not generating. Generation always happens in the decoder. GPT, decoder is the generated. Encoder part is BERT, which is just encoding the text, right? So here the encoder just gets the image, breaks it down, okay? And then gives you a mean and covariance, right? That means it basically gives you some information about the Gaussian distribution. You say, okay, I know this Gaussian. You pick sample from this Gaussian, and that gives you this latent Z. Hidden is a latent vector. You have a model that gets that Z and generates the image from that. That's the decoder. So encoder, decoder, that's what we're saying there. So these two work together. One of them to get good at breaking the data down. The other one becomes good as like a regenerating the data from that latent. And the output should be the same image technically. You compare the two images together, basically.
Sorry for repeating myself, but that Z from here, what confuses me is Z is coming from a Gaussian distribution with mean 0 and the standard deviation of 1. But over there, Z is coming from a Gaussian distribution that's being learned by encoder. So that's a little bit.
Yeah, so okay. So you can basically assume this. Let's say there are a couple of pieces. Let's say we don't have that. Okay. We don't have the encoder. And I want to just generate an image. Okay, I only have a decoder. Right? So what I do basically is that there is this Gaussian. I sample from this Gaussian, Z. I pass Z to a model. The model gives you mu. It gives you covariance. I pass that covariance basically creates this some probability, the probability value, and I continue from that. That we will see, we haven't gone through this. Like there are multiple steps to generation. That's the general view that you will see. But then if you wait, we will get to later that. All right, yeah, that's a good point. Okay, so, and again, this is just exactly what you were asking. So you sample Z from this, feed Z to your neural network that gives you mu and covariance. You generated data by sampling from that Gaussian with mu and covariance, and that becomes your generation, basically. That's the decoder part of the work. Okay. Now, there are challenges here. Well, the first challenge here is that Z is not observed. We don't know Z. Or it's itself is challenging to try. If you haven't seen Z, it's challenging to try to answer a question. What's the probability of X given Z? You know, so itself, it basically is challenging. Now, think about this. So one of the latent variable models type is actually called mixture of Gaussians. Okay, so that's one types of latent variables. Now, in basically this form of, let's say, one-dimensional latent variable or mixture of Gaussian, and I don't know if you're aware about, like, for example, if you have a mixture of Gaussian, that means you technically is a model that, let's say you have K Gaussians. So every Gaussian by default has a prior, or like, and that prior is that, so have you ever basically created a, like a visualization or a histogram or something, and you saw something like this, like a peak and down on a basically histogram? And normally, most of the time when something like this happens, if you're looking at your data and there's some category called variables, you can see that this technically is one Gaussian, this is one Gaussian, this is one Gaussian, based on those categorical variables that you have. And if you plot this in something like a 2D, basically you see something like this. Okay, so it's like a, so if you plot them all together, you basically see something like this as one contour plot. However, when you look, you see most of this area is empty and the density values happens here. That's where you have mixture of Gaussians. Okay, so now when you have mixture of Gaussian, the idea here is that you have this summation over some prior per class. I is from 1 to K, if depending on how many class you have, times basically a Gaussian for class I and variance or covariance I, depending on the dimension. That's technically means mixture of Gaussian. Okay, so one way basically here is that as from the latent variable models could be a mixture of Gaussian, and here basically what we are saying is that lambda n stands for the pi that I just wrote. It's like the prior for every Gaussian, and here you want to answer this question. So if you look at the image here, so you have this one, this image on the left, probability of X. And what we basically try to say here is that when you're looking at this ups and down, technically that means there are some latent Gaussians, latent variables, you know, and here you have Z1, Z2, Z3. On the basically Z1, Z2, Z3, each one of those are technically a Gaussian with this question. What's the probability of X, okay, or probability of X given Z equal Z1, probability of X given Z equals Z2, and so on, okay? So this is probability of X and Z1, probability of X and Z2, probability of X and basically Z3, and so on. Now, given Z2, Z3. So you have all this basically Gaussians, this is given. Now, if you put all of this together, map them all together on one picture, like or sum those like that, that becomes this blue. That's the marginal of X over Z. That means you have all this sliced Gaussian latents, and you basically map all of those together. So this is called like a mixture of Gaussians. And if you think about it from latent representation or latent models, you have X and you want to find a way to produce X, okay? Produce data point that looks like X. And what you do, you basically have this idea that, well, I think my data has K Gaussians, okay? And what I need to do in order to generate one data point is to sample one data point per Gaussian, per K basically, and then put all of those together in order to become the data that I have. Does that make sense? So it's like if you sample one here, as you see, you have the probability of X given Z was Z1, probability of X given Z2, and so on. If you find all of these latents, and you can basically get to this marginal, which is the probability of the data point itself. And that's what you want to maximize technically. If you can maximize this, that means you have learned also this really good. Okay. Now there is, of course, there are challenges here. Well, if you think about it, maybe you know the number of k that you decide itself is challenging, but also when you have a large data, like a lots of data, this is not going to be feasible. You know, this mixture of Gaussian, it's not going to be something that actually will work. The data that it will generate it doesn't look like a really realistic. So here, basically, again, what you see here, so Z is a category called, basically, that means Z could be K categories. Every category has a probability of occurring. And this is the probability of occurring per category. And this is the normal for this part. And the marginal becomes summation across all of that, basically, axis. That becomes the marginal. Now, yeah, so let's go back. Basically, this technically give us the same thing. So how do we got to this equation? Basically, can think of it as you have this probability of X and Z, and or let's say probability of data set technically, and or probability of X and Z across all your data, because we know every data points basically they are independent of each other. This is like a multiplication, something like that. And the first thing that we know here is that, well, depending on also if you do a log, this becomes summation. If it's categorical, this becomes summation. But you do a log, for example, this becomes summation. This, again, you can present it in two ways. What we have here is we showed it as probability of xi given zi times probability of, because there's a log here, it becomes log of this plus log of zi, probability of zi. Log of prior likelihood, because again, joint can be written as likelihood times prior. So when you do a log, it becomes log of summations. So so that's in a log form, and this itself, actually without log, this itself is probability of xi given zi times probability of zi. And that's this term technically. Probability of x given zi is the Gaussian. Probability of zi is the prior. That's technically what we call a mixture of Gaussian. It's just we use the Bayes theorem here. Is that clear for everyone? This basically all it says that if probability of data set becomes multiplication of probability of individual, right? So, and for one data point also, so you could also consider this for one data point. So what is the probability of one data point given one data point and Z technically? So if you think about what's the probability of one data point, you don't know Z. Z is latent. Z could be technically anything, right? In the scenario of mixture of Gaussian, we said we have K classes, correct? So, and we say that if you pick one class, class one, and let's say you get this, and you pick second class, and then you get this, and third class, you get this, and so on. In order to convert all of this to one distribution, you sum those all, right? So you do a summation across this axis, and then that maybe gives you this. That's probability of X. So that's why probability of X for one data point could be shown as summation over all of these K classes, Gaussians. The probability of that Gaussian, probability I from 1 to K, probability of that Gaussian, this is pi, times a Gaussian for X, which was basically we just showed as P of, P of X given Zi. So that's a Gaussian per class, multiplied by the prior of that Gaussian, sum across all. So that becomes for one data point. Multiplied across all of the data points that you have, and your goal is to maximize this overall. That maximizing the likelihood, basically. Is that clear? All right. So Now, what's the generative process when it comes to mixture of Gaussian? Well, you just pick a mixture of component K. Like I say, you have K components, sample basically from that, generate data points by sampling from the corresponding Gaussian, and then put those together. Right, that becomes the process. Now, you can use this for something like clustering. So if you have learned the posterior probability of Z given X, that means you had the X and you find what's the probability of Z given X. If you learn this latents, you can cluster the data in the latent space. That's actually one of the really good reasons for using like autoencoders, not for just generation, is because if you learn the latents, data that normally they are high in a general form, data are in a higher dimension, but data, they normally have a lower intrinsic basically dimensionality. If you learn the latent representation, you technically have learned a compressed version of the data in a much lower dimension. And that's normally a better space for doing something like clustering in compared to a clustering over the original data. So one of the reasons we use these types of model is for clustering, because if you learn the good representation, like a latent representation, then you can do clustering. And you can basically use it for unsupervised learning. And it has some caveats for that, but still like possible. But this mixture of Gaussian mostly will fail again, because if you apply to a large image data set, it's hard to basically, they hardly can generate good data. Now, that's where we basically go to variational autoencoder, and then the idea here is that, so here what you see on top is autoencoder, the first one that I draw, and on the bottom is variational autoencoder. So image comes, goes to this encoder. Encoder basically gives you this mu and basically covariance. You sample from that, you pass it to the decoder, and you generate the output basically. This is during the training. Okay, that's important to remember. When you are done with the training, if your goal is to do generation, you don't need the encoder anymore, because decoder is responsible for learning to generate. If the decoder has learned to generate from sampling from a Gaussian, then all you need is a Gaussian to sample from and pass it to the generator. But if your goal is to do something like likelihood basically estimation, like, or someone give you a data and say that you want to detect how likely is this data, then you need encoder, decoder at the same time. Okay, so if you just want the generation, after training, you focus on the decoder. Now, a couple of terms, as we go through slides, Q basically will represent the encoder, P will represent the decoder, basically. Okay, so just remember that. Okay, so the thing about the variational autoencoder is that it's a nonlinear latent variables. So that's one thing about it, is nonlinear latent variables. The second thing is that it's for continuous basically data. So nonlinear and continuous data here. Okay, so now similar story. Your latent variable, we assume it comes from a Gaussian distribution with mean 0 and basically variance phi. Then when we go to the this probability of X given Z, which is the decoder, basically part of the work, we also model that from a Gaussian, similar to what we saw, this Gaussian, the mean of the Gaussian, there's a difference here. So we said the mean of the Gaussian will be generated by a model. So this part, this will be generated by a model. But for the variance, or for the basic covariance of the model, we are enforcing it. So what you see over there says variance times I. That means an identity matrix with variance repeating. That's what it means, the variance times I. Like a diagonal matrix of variance, same variances. So, and again, we will see that this I will change this representation depending on types of model. So, okay, and then that F is basically parameterized by phi, which is a neural network. So, Now, what you basically you see here is your goal is to find what's the probability of X. You know, that's what we're trying to basically maximize for. And we basically, we are in a continuous space. So it's not summation, it's going to be integration. Because again, VAE again is continuous, nonlinear, basically latent variable models. So it becomes an integration. You have probability of X given Z times the prior of Z, dZ. And in order, so that's the marginal technically, right? Because you do over Z, this is marginalization of X given Z. That's how you get P of X, okay? Now, if you want to map that to this image, think about what was the definition in VAE so far. In VAE, basically, we said that when you have Z, okay, technically, Z basically, we say that it comes from a Gaussian with in 0 and I. Then we also said that probability of X given Z comes from another Gaussian with some mean that we will find it via a neural network. And the variance is for all of them fixed, sigma 2. Okay, so you see the term probability of X given Z. So that means this is the normal Z. Okay, so let's say I want to find the likelihood, the marginal of X. Okay, what do I need to do? I need to basically sample from Z one time. Okay, then after I sample this Z and I say that I can find the probability of X given whatever sample Z I have comes from a Gaussian with some mu for this Zi, let's call this Zi, and sigma 2 variance. Okay. Then I pick another sample. I repeat the same thing. So on and so on. Okay. So every time you pick one sample and you pass it to this one. This is what you see in the image. So first one, you have this basically hyperspace. You sampled one Z, and this region that you see, this region in the image, that's where the Z sample was. That's where Z could come from this space. When you sampled it, this is the Z that you got. Z could come from here, you sampled Z come here. And when you repeat this process, and if you put all the Z's together, they look like this basically. Okay, that becomes the marginalization of X over all possible Z's. Okay, and technically this is called infinite weighted sum of basically spherical Gaussians, because these are all spherical Gaussian. What's a spherical Gaussian? Which one is a spherical Gaussian? A Gaussian with what? Variance I, right? Spherical. Circular, basically. That becomes a spherical Gaussian. That's why these are all spherical, because of that. They all look alike. Every time you sample, it's going to be same shape. If you keep repeating this sampling and you put them all together, this becomes the marginalization. Okay, so now, what's the generative process? So we start from the left. This is the Gaussian. You sample from it. This is the sample. This data point is the sample that you got. You just randomly sample from this Gaussian, and this is what you get, Z star. Z with dash 3. Then you go to the second step. This is the likelihood. The likelihood basically says that I pick this Z, what is the chance of X given that Z? And this is basically what we got, the spherical, right? If you keep repeating this process back and forth, you basically get this. That's again the marginal. So that's the same image we saw before, but in 3 steps.
Can I ask, what is the light thing in the middle at the end?
That's the marginal of X. So what's marginal? Let me tell you that way. So let's say, let's say there is a image of Ashcan, and Ashcan is the part which is the mouse is pixels missing, right? So Ashcan is either happy or sad or something. And we want to replace those pixels. There are all possible pixels we could put there, correct? All possible, right? Then the marginal basically becomes that if you keep basically repeating the sampling and replacing, right? Marginal becomes the probability of that full picture, given you went over all these basically pixels to replace. If you keep sampling and keep replacing here, the overall image that you will get, that becomes the marginal. That's the region. That's the basically sampling all over the entire space of Z. Z is your hidden. You sample over all of it, infinite, and this will be that. That means the image, the part of the image that's missing, if you do infinite sampling, comes from this region. Okay.
Isn't the picture of me just one picture?
Yeah, this is for one picture we are basically talking, 1x.
But then that missing part is going to be one. Then why it is so many infinite?
So, okay,
What if this is
so no, the pixel itself, what is the pixel? In order to replace that, think about this. How do you decide what pixel should go here? So if you just randomly put pixel back, so it doesn't work. You need to basically be able to look at this image and say that I sample from some latent, and I could sample 100 times. I could sample infinite times, right? And every time I sample, I try to basically put back and say that, okay, what will happen? Okay, what will be the outcome? So you keep repeating this sampling and basically generating. If you put all of those generation on top of each other, okay, that becomes the marginal for that basically part of the image, that basically that image over that missing, over that latent set of variables. So the idea of marginalization is like, what will happen if I keep repeating this for this certain variable? Like you have x and y, and you want to see what's the probability of x, but you have a variable y.
Why you get rid of y?
That's correct. So that's the marginalization. You have lots of z, you want to get rid of z. So in order to do that, you need to sum over z basically, right? So that becomes the idea of marginalization.
What if like the image we get at the end is not exactly the match of the original image?
So this is like that was just one example, but this is like a learning.
Yeah, but like even after we, if we assume like we train on the on large data set, and if the decoder at the end is not able to generate the original image.
Change the algorithm. It's possible. You know, there are lots of this stuff. It's not like that whatever you see as algorithm here will work definitely. There's a high chance that you use an algorithm and at the end the result of the algorithm is not coming good. Actually, there are we will see quite challenges with all these algorithms. It's not that easy to make this type of generative models. They don't work that easy basically. If they were working, that we wouldn't keep coming up with a new version, right? But yeah, so that's possible. It's highly possible that you train and it doesn't work.
Apple and Samsung, that's what I was asking.
Yeah, I mean, as reality is that, you know, it's not that easy to generate. I'm going to start a simple example here. So let's go back to this one we saw in autoregressive before, where you have these images and the upper part is missing. Okay, upper part of the image is missing. If you think about it, what's the connection of these to latent models? The green is latent, right? And the black is the image basically that you have, or the bottom part of the image, basically, the black and white. That's what you have. The upper part is the latent, which is the part is missing. So your goal is that to be able to generate that, you know, to basically recreate the image. Now, let's say you have some sort of model, pixel CNN, pixel RNN, that is like an autoregressive, sequentially will generate this for you. Now, for this data set, the marginal probability, this is for one data point, the one in the bottom, probability of X, this image, be equal to this full image. That means you filled all the missing one, given some parameters, comes from basically this term. Here, as you see, we sum again over all possible Z. This is the marginalization, right? This term and this term are the marginalization. But now, if you think about it, so how many colors you have here? 2, binary. Let's say you have 20 pixels. Okay. If you have 20 pixels and you have 2 options per pixel, how many combination you need to go over? 2 to the power of 20, right? See how expensive it is to just calculate the marginalization for one image. So that's the challenge here. It's not that straightforward to basically generate those images, even for a simple binary image, basically. So, and then so you can basically show the total likelihood basically over across all your data points, which we actually added here. It's going to be multiplication over all your data point. Then you apply log to this, take the log inside, becomes summation. And then for every data point, you need to loop over all possible missing pixels, basically. So if here basically what it says, if you have 30 pixels missing, you need 2 to the power of 30 basically operation per data point. Now, if you have a data set of size D, the number of iteration is kind of like out of control. It becomes really expensive, something like this, to generate that data set or make that model work. So now let's go back to the continuous basically space or the variational autoencoder. And our goal over there is also to do similar thing. We try to maximize the log likelihood. Here, there's a difference that basically we say that, well, I mean, in all of them, the log likelihood term is the same thing. It's the log over multiplication of individual data point because there are IID. So that's the first one. And when we apply log, this becomes summation. This part is individual data point because there are IID. And that will convert to this times that, which again, anytime you have probability of X and Z, you can show it as probability of X given Z times probability of Z, or you can show it as probability of Z given X times probability of X, depending on this problem that you have. All right, these two are the same. So here what you see, we show it as probability of X given Z times probability of Z. Okay, and probability of Z, as we said, is kind of like a Gaussian with mean 0 and variance I. And the probability of X given Z, the mu comes from this, what's called neural network. And the variance is technically fixed across all of those. So there are some challenges with partially observed data, where the first one is that they are basically they are not decomposable by variables. What does that mean? Because you haven't seen the latent variables, you cannot decompose, you cannot break down these images with respect to basically those variables because they are unknown. They are non-Yoni model as a function of theta or phi. And the reason is that this part of the equation is multimodal technically because you have mu and covariances. So they are non-Uni model. That's challenging. And the third one is that the gradients are really hard to compute, but we will see. It's not that straightforward to calculate the gradient for these models. And the idea here was, okay, how could we make this easier to solve? And there were like three ways that we can basically do that. One of them was that, so we wanted some way of solving this problem that it doesn't require us to go over all possible combination of Z, because that's really expensive. If you think about it again, all possible hidden latent that you want to sum over for one data point, that's really expensive. How could we reduce that cost? And also we want something to be cheap. We want to find a way that basically reduce the need for going over everything. We also want it to be cheap. And then this idea of this sampling ideas came to mind. Is like, so what if we do Monte Carlo sampling? What if we do importance sampling? And the third one, what if we do estimated lower bound or elbow technique, basically? Okay, so that's basically what we're going to talk about now. Now, we're going to start with the Monte Carlo, which we previously have talked about it. But the idea in Monte Carlo is that if you have a distribution that's unknown, and you cannot answer a question with respect to this distribution, you sample from it, put it in a bucket, they all become uniform, and the probability of all of those becomes the same. So basically for continuous or discrete, if you have this distribution, you can, using Monte Carlo, represent it basically this way. So instead of this coming from some unknown distribution, because you sampled from Monte Carlo, this becomes a uniform distribution. That 1 over z, that's the probability per data point. And I'm going to talk about what's the z behind it. You can show that as this expectation also over that uniform. Now, technically, in a general form, if let's say I have this distribution, and I sample k data points from it, and all this k together becomes uniform. So then using this uniform distribution that you have, you find that expectation value, which is the right side of this part, the last part, this expectation. However, if you think about that expectation in compared to the first question that you were asked, so at first you were asked this question, what is the likelihood, or basically the likelihood term, or the density basically of this, you know? So that was the question that you were asked. And you were like, I don't know it, I can't keep sampling from this. So instead of doing that, I have some samples, put them here, use that sample to estimate this expectation. But one thing that's important to know is expectation and this are not the same thing. This is average, like a weighted average over some samples, that is across all the data points. So what you need to do in Monte Carlo to multiply this by the size of the data set, so the z that you see behind it, in order to re-scale that weighted, like average, to be back to the basically proper, basically density value. So over there, both of them are z, but technically the second one, maybe this is better. Yeah, so the second one technically should be k. K is the sampling, but z is always fixed, is the size of the actual data set that you have. So again, you just use the sample, find the weighted like expectation, multiplied by the size of the data set, and that will present this part for you. That was, you didn't have it at first. Is that clear? Okay, so that's Monte Carlo for also here for both softwares basically. At first is this, summation and integration, but because you sample, that becomes summation for both of those anyway. So, well, there are some challenges with Monte Carlo. Well, one of them is that curse of dimensionality. It's like what happens here is that most of the time after this, you solve the problem with Monte Carlo. For every data point, the probability value that you get is end up being really low because the dimension is really basically largest part. So the chance for every data point, even if the data point is really likely from the actual training data, you get a really low probability value for it. So that's one thing. The other thing is that rare region may dominate the total distribution. That means something that was really off is really rare, not so we have two types of rare. One rare is rare and important, one rare and basically anomaly. So this basically means the rare and anomaly. The points that they are not important, but they were really far from the rest. They actually impact the Monte Carlo. They can basically dominate the space. And the other thing is that, well, uniform sampling is not a really great strategy. If we just assume everything is uniform, you know, that sampling it's not a good strategy here. Right? We still have time. So that's where the next thing comes and becomes important sampling. So important sampling on the other end the idea here is that, so we have this unknown distribution, similar to Monte Carlo idea, but here, instead of we just sample from this and assume they're uniform, in importance sampling, you introduce a new distribution called Q, and you basically say that I propose this distribution Q, and this Q supposed to be that P. So I propose a new distribution, and my goal is to make this distribution Q as close as to P, the unknown distribution that I have. But why it becomes importance sampling? So you have this distribution that you don't know it, okay? Then you bring a distribution Q, which is known to you. So you know everything about this distribution. Your goal is that for every data point, for example, you sample from this, the known distribution, and your goal is to generate the data. While the data basically latence comes from this one, but you don't know this one. So the idea behind importance sampling is that I keep sampling from this distribution, the Q, but not every region of Q is important. Some region of Q, when I sample from, they will lead to a high probability for the original data. When I find a region that will lead to a good result, I keep sampling from that, important sampling. If I find a region that's not important, I don't sample from it. So you come up with some proposal distribution that you know about it, and you start sampling from that to regenerate or whatever you are trying to do. And whenever you feel like I sampled and it was a good result, I will keep sampling from that region. If it's not bad, if it's not good, then I'll basically go to a different region. So that's the idea behind the importance sampling. You still do similar to Monte Carlo sampling, but it's not uniform sampling. It's based on how good is that sample for the task that I have. And I propose a new distribution. In Monte Carlo, you force it to be uniform distribution, basically. So this just summarize basically what we just talked about. So this is basically how importance sampling works. It's kind of like some manipulation. So all you are doing, if you have a basically summation over. So here we have. Remember, you have this Z, the latent variables, and we basically say is that probability of X comes from a summation over this. Let's call this Z equals Zi, or Zi equal I don't know, like a P. Okay. So you sum technically over all possible latent variables in order to complete X, right? You keep sampling and you're repeating, and then that gives you the marginal. And we say that marginal is really expensive. You can't keep doing this. In importance sampling, what you do, you introduce one new distribution Q. You still have the same equation. You bring a distribution called Q, multiplied by it, divided by the same distribution. So these two technically, they cancel each other, right? It's just, we introduced that. But what will happen here is that you take one of the Q's outside now, behind the summation, and leave one as the denominator to go under the P. So you basically, you add Q divided by Q, then you convert it like this. QX, or summation of QX times PXZ divided by QX. Okay. So you basically have something like that now. And what does this remind you of? Summation of Y times P of Y, P of X. Expectation. So this becomes expectation of this term with respect to that any points that you sample from this Q. Okay. So, okay, what you will see is that in order to answer this question, what is the probability of X for data put? In reality, what you needed to do was there is a Z, but I don't know it. I needed to sample a lot from that. Instead of doing that, you come up with this Q, proposal distribution, and you say that I'm going to only sample Z from here. So every time you sample from here, that basically, we show it behind the expectation, becomes expectation over Z that comes from QZ. This is QZ. Expectation over Z that comes from QZ, this sample. Then, what's the inside the expectation? The original probability, P of XZ, divided by QZ. So this technique is called importance sampling. You basically introduce a new distribution, you keep sampling from that until you find the important region of that. Is that clear?
You determine QZ.
How you determine QZ? So we will talk about that, but the idea here is that you don't want it to be challenging. You want it to be something easy to pick from, right? And that becomes the advancement that we end up in variational autoencoding. We will see in the second part of the class that we force Q to be something pretty simple, Gaussian, like a mean zero, standard deviation, and that's basically that becomes the goal. The idea here is that actually this is something called amortization, and amortization basically says that if you have an expectation, and this expectation is for a posterior, for example, and you basically enforce this Q to be something pretty simple. This really, if you basically, amortization is that if you estimate the posterior via a really simple distribution, that basically becomes the amortization. But that's the whole idea here, to enforce Q to be simple, because this is challenging, hard to find. You don't want to replace it with something hard. You want it to be something pretty simple, standard that you can sample from. Questions? Okay, all right, let's take a break and then we continue from here. Okay, let's continue. So now let's go back to basically the importance sampling here. So if we basically talked about in basically autoencoder, variational autoencoder, which is continuous data. So is this an integration over basically this term, the likelihood of the data given that latent times the prior of the latent. And when we do importance sampling, the idea will be that we will introduce a Q. It's some proposal distribution that we will sample Z only from that. And we multiply it also by this Q. So that becomes expectation over samples that are coming from this Q distribution for this term. Okay. Now, this itself, this sampling, this expectation value, is part of the importance sampling. Technically, you don't do it over every possible. Now, you only just sample maybe NZ from this QZ and calculate this as summation across those N. So importance sampling it still does the same thing. You sample some point and you repeat that. It's just the types of sampling will different. In Monte Carlo, sample from same distribution, basically all basically uniform. In importance sampling, you introduce a new distribution. You sample only from region of that distribution that are important. They give you a better result overall. So that's becomes the main difference.
We have the points, but we don't have the distribution.
So you have, think about the example that we go over. You have images, but there are missing pixels. So those missing pixels, those latent, for example, you need those latents in order to get this complete. In order for this to be high, the probability of image to be high, that means your missing pixel should be correct. So how you replace those missing pixels? you basically need some latent features. So we pick those latent features from some proposed distribution. That basically becomes the idea. Using that, you want to complete the image, or using that, you want to generate an image. The answer?
But how do we verify that it's?
We'll get there. one piece at a time. So, well, there is a challenge here. Well, of course, you know, how do we decide on QZ? Okay, so the first thing here is that if you think about this base basically form, so the posterior probability of z given x, this posterior, comes from probability of x given z times prior of z, right? And where's the marker? So we basically say that the posterior of the latent given image, we know that this is technically comes from the likelihood of image given this times this prior divided by this normalization factor, right? And for now, let's just assume this normalization factor doesn't exist. So this is almost equal to that. But why we have this posterior and likelihood and prior here? So one way you can look at this latent variables models or these types of autoencoders are that we technically trying to reverse the process of the decoder. So we're trying to reverse map image to latent. Rather than latent to image, we technically try to see that what is, like this point, this is the reverse mapping. What latent should I have in order to basically have this image, right? What is the, like you basically have image is fixed. In order to have this maximum, your latent should be good, right? So you have, this is the likelihood, this is the prior. Okay, so now if we want to think about Q, which is the place that we sampled from, so we technically have this QZ given X. So this proposal distribution that we basically also offer is going to be QZ given X, right? Because that becomes the posterior part that we're going to also focus on. So technically, this is kind of like the encoder, this part. This is the decoder. Because encoder becomes the reverse, you know, it's kind of like a z given x. You get the x, from x, you get the z. Decoder becomes the other one. You have the z, from z, you get the x. So that, the one posterior technically acts as the encoder. This acts as the decoder, basically. Does that make sense? So, that's just applications. Now there are challenges to, did I miss anything here? So challenges with the variational autoencoders and important sampling are, well, the first one is that the high variance of the estimate. So that means that these weights that you have, this basically, that can vary if your QZ is bad. So if you pick QZ wrong, this or bad means that this QZ is probably approximating that. Is we assume to be the same, but it's not good approximation. The other problem with important sampling is that the rare but important events, they won't be sampled from. Because remember what happens if we find a region that lots of basically high value data comes from there, so we keep sampling from there. So if something is rare but important sampling won't sample from that region. So that's another problem it has. Well, computational basically efficiency, these two are still expensive. No, it's not, they are not cheap. Sample efficiency, you need technically large sample size for this type of models. And this QZ, finding the optimal, a good QZ is actually not easy. You know, it's kind of like a challenge itself to decide on that QZ, what QZ I should use. Now, so that basically itself introduces a new approach for VAE. So we saw Monte Carlo, we saw importance sampling, all of those, they have their own challenges. So then there was a need for a third, basically, or approach, or another approach that it's kind of makes things easier to solve. And that's where it's the elbow technique or evidence lower bound. Now, the idea here, so this part is the same thing you saw, likelihood term. The likelihood, this becomes you apply log, taking log likelihood, summation over all data points, and likelihood times the prior. Okay, so likelihood X given Z times the prior of Z. Now, the basically the way that we can look at this so we have seen actually this lower bound idea before. One example is that when we did the optimization chapter, when we talked about using Taylor approximation, right? And we had something like this, and we basically found this using the minimum. We found the next one, then we approximated, and so on until we reached the minimum of this. So evidence lower bound idea is the same thing. So basically, what we basically say is that if we are trying to maximize, that over there is minimize, here we try to maximize, for example. Instead of directly trying to maximize, you at every time, basically you find a lower bound, you maximize the lower bound. From here, you go to the next lower bound. You keep repeating this process until you get to doing so. You get to the top one. So the idea here is that if you maximizing the lower bounds, it automatically, you maximize the value of the original curve, original basically value. So that will be, instead of we've trying to focus to maximizing for this line, which we don't know it, we just know about it. We focus on maximizing this, which we actually know it analytically. And every time we just focus maximizing these functions, by keep doing this, because, and we will talk about why, these functions are always below this line by default. By raising these functions, automatically you are raising that because they always should be below that line. Okay, so that's the idea behind the evidence lower bound. Just we keep finding this like a lower bound that makes sense, and we increase that lower bound, and we keep repeating that. Now, does that make sense so far? And we're going to talk about why that should be under the line and stuff like that. So let's just start with this. When we look at the likelihood, technically we say log likelihood, correct? This is a log function. One thing about the log we know is concave. Okay, so what do we know about convex, for example? We know convex, if you connect any 2 points with a line, any points that falls between these 2 points, the value is always below the line. That's convex. Concave is the opposite. If you pick any 2 points and you connect them, that line is always below any point above it. Okay, that becomes concave. So log is a basically concave function. That means log of this plus this is always greater than log of individual, basically. That which is the line technique. It is always greater than the line. Okay. Now, does that make sense so far? Now let's take this one level further. There is an, actually, I think we saw this before in, if I'm not wrong, in CNN chapter or something, we talked about Jensen inequality. So Jensen inequality basically says that log E of X, log of expectation is always greater than expectation of the log. Okay, log of expectation is always greater than equal expectation of the log. And let's understand this on this image that you see. So in the image, that on the x-axis, the variable y. Okay. So this is the variable y. These arrows that you see on the y on the x-axis, those are sample y. You keep sampling from this y. Okay. Y is a distribution, like a random variable. It has its own distribution. You keep sampling one data point from Y, and these arrows are the samples. If you average those samples, which we call it expectation, that becomes E of Y. So that E of Y is the expected value over these samples. Okay. Now, if you look at E of Y, and this line here, this line that you see is log of Y. So whatever is your Y, if you apply log to it and you plot it, this becomes the distribution. Okay, so that means probably something like this is better. So let's say this is Y, distribution of Y. Every time I sample one data point from Y. And if I keep sampling, and here I have log of Y. If I keep sampling, so I sample one point and I find what's the log value for it. I sample another Y, so on. And for every sample, I find all the logs that it has. It will look like that because it's a log function. So if you connect them together, that is the log of Y for every Y that you pick from here. Now, this Y has some expected value, the average Y basically. If you find this average Y on this line, okay, and this is called log of expected value of Y, because you have expected value and that's the log of it, okay? Versus if you first apply log, if you first, log of expectation, so if you first apply log to every here, and then you do an expectation over this. So here you did the expectation over Y, then you applied log. The other one, you first do log, then apply expectation average over. The second one will fall here. So this is expectation over log. So expectation, log of expectation always higher than expectation of log. Does that make sense?
Yeah.
So that's a Jensen basically inequality. Anytime you have some sort of like expectation value, and you basically want to, you basically can say something like that for it. Log of that expectation is always greater than equal expectation of that log. So what does that tell us? By default, this term is the lower bound for this. This is always higher than that. So this becomes the lower bound basically for the expectation that you were trying to find. So think about what we are trying to solve. You are trying to solve maximum likelihood. You are trying to maximize the likelihood. What is the likelihood? You had this log of this summation. You apply the log, so technically, you have probability of data set, which is multiplication of probability of individual points, for example. Then you apply log to this, becomes log of summation of this individual data points. So because you have this log, you want to find it. The problem is we don't know this to directly solve it. It's hard to find. So instead of trying to directly solve this, you find a lower bound for this, which is summation over that logs, basically expectation of the summation, and you only solve for that. If you can maximize this, that is automatically maximized. So that's the idea of this lower bound. Focus on solving something that's achievable, maximize that, when you know that will automatically maximize this part for you. Any question on that? All right, so, we have this. Great. So I draw that for no reason. So on the left is the first part, expectation, log of expectation. On the right, you will first find the log, then you do expectation over the log, is the reverse. So this line is the average over this blue. This line is the average over this, so this is always a lot higher than this one. So that's basically the idea. So, okay, so let's go back to what we were trying to solve. So we had this term, with basically with introducing that new distribution, log of this, and we will say that this is always greater than this times the log. So the log basically goes inside. That's the Jensen inequality. Okay, so this term is always greater than this term. Okay, now because we introduced this log and this log went inside, then that is kind of like this becomes an expectation, right? Because this term is expectation over Q. Q times probability becomes expectation over Q, right? It's kind of so. Yeah, okay, before I move here, does this make sense? Yeah, okay.
So wait, my question isn't properly formulated yet.
Okay. Whenever you got it, just let me know. All right. So, and sometimes if you wait, probably you get the what you're basically hoping for. Okay, so now, okay, now we're going to talk about something called variational approximation or variational inference. Okay, so that's something that basically that we use basically in VAE. So the idea here is that in variational approximation or variational inference, that you actually these two terms kind of like they used at like they kind of mean the same thing. But the idea here is that so we have this Q, which we introduced via this concept of importance sampling to propose distribution that we're going to sample from that. Now, one of your friends, you asked me that how do we decide Q? And hopefully you ask, right? So how we decide Q? And I say that the idea will be that to pick Q from something that's pretty easy to sample from, easy, And so basically, that technique actually called variational approximation, variational inference, that to pick this Q to be some simple parametric distribution that we can basically sample from. Okay, so again, that technique is called variational approximation or inference. Now, normally, we pick it to be multivariate Gaussian with a mean and a covariance basically matrix. So normally that's more common to see in VAE enforced multivariate Gaussian with mu and covariance. So now let's go back to the Jensen inequality. So the first term on top, that's the basically probability of X after introducing the log term. So again, if you look at this term, so you had this log of this term, okay? And what is that term? So technically we have log of summation probability of X, Z, and whatever is the parameters. Okay, you try to maximize this, maximizing the likelihood of your data. Then we basically what we did, we said, let's introduce a Q, okay, as importance sampling. By doing so, by multiplying it by Q, by dividing it by Q. So now that we had this, we say that the basically Jensen inequality says that, wait, you can take the log inside, and that means this term is always greater than as summation of, you take the log inside, so it becomes QZX log of PXZ phi over QZ X. We took the log inside. This term is always greater than this term. Okay. So that becomes the Jensen inequality. Now, instead of summation, sorry, this should be integration, this continues. Okay. So let me fix that so otherwise. So it's technically for one data point. This actually we still have the summation for all. One data point becomes integration. Now, this term, the lower bound, is called elbow. So whenever you hear the term elbow, it's focusing on this evidence lower bound of this basically from the Jensen inequality. Now, your objective here basically is that to find this phi, this parameter phi, somehow that it maximizes this evidence lower bound. So, or overall phi and theta, just basically your parameters. Your goal is that to find this parameter somehow that this is maximum, because if this is maximum, this is maximized. All right? So your focus will be on solving this part of the equation rather than this part of the equation. Okay?
Should be minimum actually.
Should what?
It should be minimum, no?
Why minimum? If your goal is to maximize the likelihood, right?
Yeah.
So this should be always greater than this term. If this term goes up, this goes up. If this term goes down, this, we don't have the lower bound basically. That connected, right?
Yes.
That's the aha moment. All right. Okay, so now when we want to talk about this this elbow, there are actually different ways that you can present elbow. So the general first definition of elbow is this. You have, again, some integration. This is like for one data point, technically. This introduced proposed basically distribution times log of this term. Okay, so now if you think about this, so depending on continuous or discrete, this two will vary because you can apply continuous or discrete. But in either scenario, you can break this two term down. So, and then you will see the three kind of definitions of elbows are coming actually about how you present the elbow, how to decompose the elbow term. So in the first form, or general form, we have Q Z X log P X Z. I'm not writing the thetas and phi's, just simplifying. Q Z X. Okay. So you have this summation over all possible Z. So we can decompose this by basically writing it as basically summation of Q D X P X Z minus summation of basically Q Z X Q Z X, correct? The log becomes log of division is log of basically deduction. So, and then you expand it by multiplying it by that Q at the first. Now, if you look at this term, what does this remind you of? Minus Q, so sorry, this should be Q log Q log Q. Minus summation of P log P. What does that remind you of? Entropy. So this is H, the entropy, with the minus technically. So that is the entropy. That's why what you see, this converted to entropy of Q. That means Q is a distribution. If you calculate the entropy of that distribution, that's this term. On the other end, you have the first term, which is Q log probability of Z, X, and Q. Right? So this means that if you sample from Z, after you have that sample, and this is the total image with the replaced missing pixels. This value you want to be large. So if you have this large, and you have the entropy also large, this becomes a large total. Okay. If you have this one is small or this one is small, it's kind of like the value goes down. So you basically you find a balance for it. So you want entropy to be high for a Q. What does that mean? That means you want a distribution that has high entropy, lots of variation in it for a Q. It's not fixed because you want this to be high. You also want to be sure that every time, if you keep sampling from this Q and using that sample to replace this missing pixels, the overall probability of the data, like average, like a weighted average of the image with replaced missing pixels that are sampled from Q is high. So this part, the first part, is technically you keep sampling from Q, you get Z. Using Z, you regenerate the image. Like if you do a weighted average across all those samples and regenerations, you want this to be high. and you want also entropy be high. That's how you can increase the evidence lower bound. Yes.
I follow like the mathematical reason for the entropy to be high, but I don't understand the impact of high entropy of Q. Like,
So entropy means that the amount of randomness in your data, right? So you want your data to be as maybe as sparse as possible, that you could sample from every corner of this data, rather than having a data like this is a data with high entropy, and this is a Gaussian with low entropy, for example. Right? Because the variance is lower, the lower the variance, the easier to sample from. Variance is higher, that you want it to be basically, so you want data to have a high entropy so you can sample from different regions rather than enforcing something really narrow on it, because that goes closer to the uniform at some point, right? So this is the general form. It's not the one that we use in practice, okay? So that basically comes to the other basically version, and what you can basically see. Actually, I think there was one line that I didn't go over it. So the last, sorry, I think I passed this part. Yeah. So so this part, you can write it basically as entropy, and there's this line on the bottom. So again, this is the same thing, but I just wrote it as expectation. So these two terms, the last two terms are the same. You either show it as expectation or you expand the expectation and it becomes entropy for the second term. Now, if you go to the other representation, and the focus here comes on this part. On the nominator here, you have probability of X and Z. But probability of X and Z can be presented in two ways. Probability of Z given X time probability of X, or probability of X given Z time. So depending on which one you present, the definition is going to be different. And so the first definition here, it highlights the conditional distribution and overall likelihood basically of the data. The second one highlights the basic conditional of the data over latent and the prior of the latency. Both of these are valid, and depending on the domain space or basically what you are trying to do, you can select different, right? So you will see both of those technically in literature. Now, we're going to, now we want to basically focus on the elbow and how the learning process works. So one thing that's really important is, okay, so you have this log, and this basically kind of like goes up and down. So you have two parameters. You have two models technically, an encoder and a decoder, right? So there is an encoder parameter, which is theta. There is a decoder parameter, which is phi, okay? Now, think about this. When the image comes, you basically, there are all sorts of ways that you can encode it technically. And the encoding quality depends on how good is that model, how good are those thetas. So if you're trying to overall increase this log of generation, so this is the generation part. You need to think about this lower bound has two parts. One part is how good is this theta? One part is how good is phi. Because theta is for encoding, phi is for generation part. So this evidence lower bound basically starts like this. So you come up with the first lower bound, okay? And the first lower bound is generated using technically the initial theta 0 and, for example, phi 0. Then from the first lower bound, for example, you go to the second lower bound. These are all, anything vertical movement is with respect to encoder, with respect to theta. That means you are changing the theta. Anything horizontal movement, it means you're updating phi. You're updating the generative model. So as you see here, when you go up, the phi is constant, the theta is changing. When you go lateral, theta is constant, phi is changing. So there are two steps in solving the lower bound. One step is the vertical move, which defines the lower bound region. How much lower bound space we have to move in. When you went to that lower bound region, you need to move across that region to find the toppest or the highest point of that lower bound. From here to here, which is the highest point. That's the generative updates, basically. You get to the highest point, then from there, you go to the next lower bound based on that theta that you have. That gives you a region. Again, you move lateral on that region, update the phi, and repeat the process. So it becomes, that's the whole idea. There's encoder, decoder via basically lower bound. Is that clear? Okay, so
We know those color bounds, they don't as the main probability.
that's a proven like a quality of this Jensen inequality, for example. That expectation, that by default, it's proven that expectation of log of expectation is always higher than expectation of log. Right, so this was this point that we went over. So it's always below it. You can prove it yourself. It's always below it. So it cannot pass it technically. And here, because when you think about the maximum log likelihood, you have that log. Because you have a log, you know that log overall that you're trying to maximize is always greater than something lower than it. And that something is whatever was the term. So you're doing a log of something of that log. You're always greater than that. So these curves that you see are when you took the log inside the equation, basically. You always have a higher value than those. But what you know is that if you keep increasing these curves, because by default, they always should be below the original function. If you keep increasing those and you are successfully increase those, you should get to the higher value over the original function. Right? It doesn't happen in reality, but it's possible that you get to the point that this curve, basically theoretically, is equal to this top point. That's mathematically is possible, but in reality doesn't happen, basically.
It makes sense, but like just the logic of the sentence that if A is always greater than B, then shouldn't the minimum value of A still be greater than the maximum value of B?
A is always greater than B. That is valid if you're converting to numbers to them.
Yeah.
Right? But if you're converting to functions, that functions has a variable output or dynamic output depending on input, that's not the case. That minimum of A should be always greater than maximum of B. So here, basically what you are saying that means that this should be greater than that.
Like I understand. This logic is why I was struggling to understand.
Oh, okay. Does that make sense now, do you think?
It does, yeah.
Okay. So, all right, so this, now the next terminology we're going to talk about is actually called tightness of bound. So the idea basically here is that we basically says that this bound, this lower bound is tight when the estimation that we have is pretty good. That's the idea of tightness. It's like means that you have a really tight basically estimation, and that's called tightness of bound. So if you think about the posterior, which we say that comes from likelihood times prior, overall, basically, if you think about the whatever normalization you do over this zi's that we have, this gives you this posterior like overall. So you have z. Let's say you have infinite z. Okay. So if you basically normalize this infinite z, it basically gives you this overall z. It's just so this is per z. You have n, like if you think about, you have z1, you have z2, and so on, right? If you put all of those together with respect to z as a posterior, you get this. But when we say normalizing it, what does that mean? Individual z together, like this z is a distribution, this z is a distribution, so on. If you put them on top of each other, for example, together, they are not a valid distribution. They don't sum to one, they surpass one. So when we say normalizing it, that means that you need to ensure that if you put all of this together, they become a valid distribution, they sum to one. No, you need to normalize that. Otherwise, each one of those are different. Now, for example, in this image, if you think about the sample x star, so this is x star. See this blue point on this image. So you have a sample image. This is the x star. Then you look across first dimension, first latent variable z, and you sample from it, and it comes from this region. Then you sample from the second one, comes from region, and so on and so on. This was the marginal, but this is the x. However, if you look at these two latent, z1 and z2, z1 is more likely to generate the data point in compared to z2, right? So every latent has a basically chance of generating that. That chance will be basically represented this way, the posterior. What's the probability of z if I give you this x? And that comes from, what's the probability of this x if I give you this z times the prior of z's, right? So it's kind of like some of the z's, they have a higher chance of, for that data point, some of those basically have a lower chance. But overall, you want to be sure that you normalize all together in order to get that posterior. So it becomes a valid distribution. Now, if we go back to the elbow, so this comes back to this second definition of the elbow. So P of x and z, basically what we do, we're basically going to show it as qzx log p, either zx or xz. Zx phi times probability of x over qzx. So we broke this term into conditional over x times prior of x, okay? So this is the second definition of elbow. Now what we do, we just take this term out, take this term out. So this becomes summation over z q z x log p of x, or p of x given phi, minus summation q z x log p p z x phi over q zx. So the first term will give you this term. Why? Because what we are saying here is that p of x is the prior over the data, right? If you keep sampling from z, it doesn't impact the prior over the data, right? So z doesn't have an impact, so technically this becomes just log p of x. So that's why the first term is just the log likelihood of the data, log of the x. Because again, it doesn't have any, z doesn't have any impact over the original data. The second term on the other end, what is this term? Scale divergence between q and p, right? So this becomes minus scale divergence between q, zx, and p, zx phi, okay? I think that was your question. So how we are learning this, so this becomes our elbow, which we are trying to maximize This is our lower bound, which we are trying to maximize. Now, if you look at the image here, the blue line is log P of X is fixed. You have a data set. The probability of that data set, the log of that is fixed. It's a fixed value. Okay? So this side is fixed. This side is the Kale divergence, right? So if, and this is technically the elbow. So if Kale divergence is, in what scenario do you think this Kale divergence becomes minimum? If these two are the same. So if Kale divergence is minimum, or technically zero, the elbow becomes log P of X. So if this is the elbow, will be exactly equal to the blue. So but that's what it means by maximizing the elbow. So if in that scenario, because you force the Kale to be zero, you made your elbow to be maximum, and it's going to be exactly equal to the probability of the data. So that becomes the learning in this scenario. And this Kale technically basically tells you that the difference between the original posterior distribution for the latents versus the distribution that you presented as a proposal distribution for Z. So instead of using this, you introduce that and you're using this. But if whatever you introduced here is as good as this, as close as to this Kale goes towards zero. That's the goal that you have. You want to find this somehow that this becomes small possible. Is that clear? So that's the first definition of elbow. And when we say tightness in the elbow, basically it's tight if this goes zero. This Kale goes to zero technically, because these two become the same term. So now the third definition of elbow is when you switch the order. So instead of writing it as a likelihood of Z given X, you basically write it as probability of X given Z and phi, for example, times prior of Z. You write it the other way around. And do the same thing, basically expand this. So you have UZ X log PX ZQ minus basically Q ZX log PZ over QZX. So this is again a Kale divergence, but this term is a Kale divergence between Q, the Q that we estimate as a posterior, and the prior. In the previous scenario, it was a Kale divergence between Q and the posterior of Z. Here we focus on the prior of Z. There's a difference in the focus, what we are basically caring about. On the other end, the first term, this technically means reconstruction accuracy. You want the elbow to be maximum, correct? You have a term minus another term. They are both positive here. So, well, no, they're not both positive technically. But so this one, you have a minus, right? So your goal is that to basically reduce this as much as possible, correct? Your goal is to, because you do this minus that, to increase this as much as possible. Kale divergence makes sense. You want to minimize it. This, you want to maximize it. So this becomes reconstruction accuracy. Why reconstruction accuracy? You have a missing image, missing pixel, for example. And you basically say that I keep sampling from Z. Okay? Z comes from a distribution. I keep sampling from Z. Using that Z, I complete the image. Okay? That's a different samples Z. You complete the image. Your overall goal is that based on the samples that you receive from Z, this reconstruct version of the image that you have to have a high probability. So this term will act as reconstruction, basically accuracy, which is really difficult to find. Why? Because you still need to go over all possible Z's technically. It's not that easy to find that. Now, there are challenges again here. It's like anytime you have going over Z or technically integration over Z, it becomes challenging because you need to go over all possible basically scenarios. Now, and second term, it just measures how closely these two terms will match together. Now, so this is like a third definition. Now, if we go back to this example that we have when we are trying to find these missing pixels, well, the reality is that it's kind of challenging. The direct computation of these missing pixels are not straightforward. It's like it's going to be expensive. And basically, we talked about we go over the variational approximation. That means or variational inference. We introduce a new distribution to be easier to sample from. And well, this is just summary of what we just talked about. Basically, we say that as part of amortization, we show that to be a simpler, basically, distribution. We pick it multivariate Gaussian with mean and covariance. We replace P with Q. This is the amortization part. And then we try to basically minimize the KL divergence between, depending on which approach you use. You do either KL divergence between Q and the posterior of Z or Q and the prior of Z. That's the two KL divergence. Now, this will be the overall idea of the KL divergence is that if you're calculating this KL divergence between these two, this is a good estimation, but KL divergence will have a hard time if your posterior is multi-model. So if you have a multi-model posterior in your data, KL divergence doesn't do a good job. If you have a uni-model, then KL divergence basically is a good strategy to use. Now, again, it's just a random example, but if you think about this missing pixels, because it's binary, you could have theta to be 0.5. It's like a Bernoulli, right? And the chance of flipping becomes 50%. You could have all to be 1, then all becomes black or all becomes 1. That's not good. Basically, you could basically have something to be like almost 1 for if the top of the digit is 9. Basically, you put all black. Like you can come up with some sort of like conditional for this. This is just a really like a simple scenario. But the problem that we have here, the note that we want to refer to here is that quality of this approximation that we have, it all depends on what we saw in the image. If you only see a really small portion of the image, then the rest that you are trying to generate is not going to be that easy. So that's really important how much you have seen. And the other thing is that the initial stage of learning in these models could easily diverge you from the actual learning. So that's kind of like important to remember. Now, we're going to reformat this variational autoencoder. So this is what you saw before. There's an encoder. Encoder gives you this mu and covariance. Using that, you sample. So you come up with this Q. From Q, you sample Z. From Z goes to the decoder or generative. It generates for you. Then you have this elbow loss, which elbow loss has 2 parts. The KL divergence between Q and P, depending on which one you use. Here is the third definition. And then also there's the first part, which is the log of probabilities. So you want to maximize that, you want to minimize that. By doing that, if you minimize this, maximize this, elbow loss goes up. Okay, so that's the general idea. Now, any question before we continue? So, actually, the third line also said that the loss function negative elbow. So it's more likely you will see negative elbow to just do a minimization instead of maximization. We just multiply by negative. So Now, let's go back to the definition of elbow. So that's the one that we wrote over here. So we have this term. And here, basically, what we can do for this one, we can apply Monte Carlo sampling to sample in order to estimate that value. And for the second term, which is the KL divergence, if you think about it, what we are trying to do, we are calculating KL divergence between two Gaussians. This is a Gaussian with mean mu and covariance. This is a Gaussian with mean 0 and variance I. And this is the formula for KL divergence between those two. So this is a KL divergence between two covariance, one with mean mu and covariance, the other one with mean 0 and covariance I, basically. So that is a fixed equation, basically. If you do the third definition of elbow, that the one on the bottom is the KL divergence between the two distribution. The one on the top is using a Monte Carlo to estimate that probability value. Now, again, this process summarizes again the learning. You start with basically some sample, you find the mu and the covariance, you pass it to the model, model gives you some G, it's like an encoder value. You, using that G, basically you sample from that, you get some Z star. From Z star, basically you generate some data using the decoder, but also you calculate the reconstruction loss and you calculate the KL divergence, the two. Using that, you update theta and phi. Updating theta and phi moves you to the next state because it gives you a next theta, next phi. You go there, move, and you get to the point that you cannot surpass that value. It's kind of like you reach to the top. And that becomes the overall learning process basically here. All right, so now if we want to put all of this together and write it with respect to the maximum likelihood estimation. So our goal was to find this log. We defined on the right side, basically this is the elbow. We defined, this is always larger than the elbow. Then we pick this as an elbow. We basically wrote it here. So this part can be written as which is what's called entropy. Okay, H is entropy. You can also again write it this form as an expectation. So these are all three are the same. Three in the line, they are basically the different way that you can present this. And overall, our goal is that to maximize the log of this for all data points, which is the same as maximizing the log of this, this loss or the elbow for all data points. So this the same thing basically. Now, there is a challenge here. So if you look at the last line, when we are trying to maximize for these parameters and D, we say that this is always larger than this. This is the lower bound. The challenge here is that for a fixed phi, which is a decoder value. So phi is the parameter for the decoder. So for a fixed phi, so let's say you have m data points. Okay, you have m data points, and you want to maximize the likelihood for m data points. So here, phi is fixed. Phi is the decoder. So the decoder parameter doesn't change with respect to different inputs. But the encoder, unfortunately here, the definition is that the encoder for every input has its own parameters. So that's why you see theta 1 through theta m. So if you have m data points that you want to encode and decode, you have technically one theta per, and theta is a high dimension, per data point. For this image, you have one theta, for this image, you have one, and so on. But for the decoder part, it's not like that. You only have one model, one neural network that just the decoding for you. So the challenge here is that it's not going to be scalable because if your data set is large, then you keep basically adding thetas for the encoder part, for the latent variable part. Okay, so that's the definition so far is basically having that hard time because again, we have one theta per data point. Now, so there is a technique here we basically use for learning and updating basically these types of model is called stochastic variational inference. So It's a technique for optimizing like an ELPO for every one data point at a time. And so basically, so this is the ELPO, what we saw in the previous slide. So you try to maximize this, and SVI, basically what it does basically something like this. So you start by initializing randomly phi and thetas. You sample some data point from the data set that you have. Then you basically need to, for every data point, one data point at the time, so xi that means one data point, you need to calculate this value. But what you need to remember is that for every data point, in order to generate, there are a series of latent variables that you could use, series of z. So you basically, this is an expectation over z. Okay, it's important to remember z is not fixed, z is hidden. You could pick from z from a distribution, right? So you keep sampling from that, and you could basically calculate this expectation. But instead of just repeating that, we do something like, for example, Monte Carlo sampling. So we pick maybe k of those, kz, and we calculate this value across k of those. Then we basically find this elbow, we optimize it. So we find, basically we update the value of theta, our previous estimate of theta, using something like a basically what do you call it, a gradient ascent. So basically you just increase it going up. Then when you basically repeat this until you get to the point that, you know, theta doesn't change, it's like a vertical you cannot move. Then you go back and you update with respect to phi. So whenever you couldn't update anymore with respect to theta, which is the encoder, you couldn't enhance the encoder anymore, then you go to the decoder, and then you update the decoder. So why? Because they both need to learn to work together. So encoder need to learn to encode, decoder need to learn to decode. And this error backpropagates basically through all of those. So then you go to the decoder and you basically update the decoder value. Okay, so that becomes the, so this is the gradient part. I think I'll give you the homework as part of your homework to calculate the gradients. I was planning to do it on the board, but we don't have enough time, so I'll give it to you to solve. Okay, so now, so SVI basically, it optimizes elbow for one data point at a time. There is a big challenge, these types of model they have, and that is that taking it back propagation, differentiating through a stochastic node is not easy. What's a stochastic node here? If we go back to this neural network that you see, what do you think is a stochastic node there? Which part do you think is a stochastic? Which part of Z? Why do you call Z stochastic? Because it's a sample, right? Z is value that you get for C is a sample, basically sample from the Q, right? Backpropagation through sample is not a straightforward task. So this model, they basically have a really hard time in order, it was really hard to train these types of models because of this stochastic node in the graph that you have. Okay. Now, so the idea was that how could we improve this? How could we get rid of that that stochastic node, but we also still do the same thing? And also, how do we show that we have some sort of like a tractable computation for our model? Now, the next idea is kind of like, well, we are going to do something called reparameterization tweak. Okay, so that was like a way that to improve that this variational autoencoder and get rid of that stochastic node. The reparameterization tweak basically says that. So previously, when you had Q, what did we do? We sampled from Q, that gives us Z. Now, instead of sampling from Q, Z has a fixed formula. So we don't sample Z. We basically, when we get to this part, we have a mu and we have a covariance. We base on that, we find Z. The only difference that we have, there is this epsilon. So epsilon is a is a noise basically. So every time we want to generate a z, we do mu plus covariance basically to the power of 1/2 times some random noise. So this becomes a deterministic basically node instead of a stochastic because it's no longer sampling for z. Z is a fixed value. Now, when you backpropagate, you just take a derivation with respect to this.
Still, the epsilon itself is a sample of.
But the epsilon is it's a noise. You don't optimize for that.
Oh yeah.
You just basically you don't take a backpropagation with respect to the epsilon. But this basically solved the problem of sampling from Z because now you have a fixed formula you can backpropagate through it. So this becomes the another idea in basically variation logic encoder and famous is called like a reparameterization trick, which because it's kind of like a trick because all we did we still technically if you think about the concept of sampling, it's really possible that you pick from mu and some range around the covariance. We just formulate that here. Okay, it's like a fixed formula. So, any question on that? So, yeah, so that becomes the idea. So this is the definition of Z. And again, the epsilon is just some random noise that we add on purpose. Now, now what basically we're going to do is that we're going to introduce just some, we introduce one new definition here to just make this.
So if Z was deterministic from the start, like if you could just derive it from a formula, then why did they come up with all the distributions and everything?
This is not deterministic.
The formula, what?
No. So we didn't make Z deterministic. Z itself comes through a large process. So you go through the encoder gives you a mean, gives you a covariance, and then based on that you find Z. Previously, we sampled Z from here. Here we say Z comes from this value. It's still finding mu and covariance are more important than that because if you have a bad mean and covariance, then you cannot find a good Z. So you still need to go through all this learning process in order to find that. As I said. So now in the reparameterization trick, basically what we do, so on the first line, what you see, that's what we had before. Expected value, sampling from Q, log of this, minus log of that. Okay, which you can present also this way. Okay, so here what we do, we introduce this function called R, and R means this function basically. So instead of rewriting this, okay, this part in the basically bracket, we just put R. Okay, so also written here, R equal to that. Okay, so we haven't introduced something new. We're just reformatting the variables. So technically, this as part of reparameterization, you sample some noise, then you calculate Z as the following equation, and we can show that as G. So if you see G, epsilon, and theta, this means this equation. Okay, it's just a terminology. And then this is R, which is that one. So you basically rewrite the same thing just based on R and G. So this term, expectation, you might see it as this. Expectation from sampling a Gaussian noise, calculating RGE, which is, this is R, and G stands for Z. Z value comes from G function, comes from mu plus variance or covariance times a noise. It's just a renaming of the variables. There's nothing new added there. Okay, just so. Now, if we basically continue with the same thing, so this is just a comparison for you. So on top, we have direct sampling. In direct sampling, look at the challenge that we had. For calculating RZ, what was RZ? RZ was that this, minus this is RC. Right? So if you drop the Q, technically, so this term, log minus, what did we say, K log QZ, log QZ. Yeah, okay. So this minus that, it's, so we previously what we were doing, we were calculating the expected value of this term by sampling Z from some QZ. So you keep sampling Z from some distribution and calculating this error, the elbow. And we call this RZ. We're just going to call it RC for simplicity. Now, in the direct sampling, the first one on top, the challenge here is that in order to calculate this, you need to sample Z from this distribution in order to calculate this, correct? In order to calculate this expectation, you need to sample Z from this and keep repeating it in order to calculate that, right? In the reparameterization trick, instead of sampling Z from there, you sample noise. You only sample epsilon noise, pass it to this model, which is this equation technically. It makes the problem much easier because you don't sample from Z anymore. You just sample from a noise. You have a model that gives you have a mu and this variance. Using the noise, you generate Z as a deterministic value, pass that Z to the decoder and continues. So reparameterization trick make this much easier in compared to direct sampling because here you need to sample data, or whether you just sample noise and using the noise generate the data. Does that make sense? Question?
I don't understand the impact of doing this again.
Yeah, so the first thing to just go over again is before introducing reparameterization, you need to sample Z from here. When you do backpropagation, you cannot backpropagate through this easily. This is sample. So reparameterization gets rid of that sampling, converts this Z to a fixed formula. So you can backpropagate through that. Additionally, in order to calculate this expected value, instead of sampling through Z, you just sample from a noise, Gaussian noise, and you just generate with respect to that. So it makes it computationally much easier. Now, we can basically apply Monte Carlo estimation here to estimate those values for basically for the gradient. So this is the gradient of this term with respect to theta. You can sample it using basically Monte Carlo. That means if you do Monte Carlo, let's say you pick data points, you calculate the gradient per data point and average it. So that becomes the basically average of gradient. Instead of gradient of average, you do average of gradients basically. And still you have this loss function, direct sampling, and with reparameterization, this becomes this. You can do same thing over this one instead of this one basically. So this is what we had before direct sampling. This is what we have reparameterization sampling. So instead of solving for that, you just directly solve for that. So this is the same thing that we have. However, we haven't answered the problem that we previously said. We still need to find one theta per data point. This is still fixed because that means that the encoder still basically needs to find the theta per data point. The decoder is fixed. Now, the last thing basically came to the concept of your autoencoders, variational autoencoders, to improve that idea to not need to learn one theta per data point. And that's the idea is the amortization. So the amortization basically says that, hey, instead of basically learning this part of the encoder, which is that posterior basically concept, okay? So instead of doing that, let's use one neural network that estimates all those parameters. Doesn't matter what's the image, what's the data that we are passing. Instead of learning one parameters, one theta per data point, we will, similar to the decoder, we will have one neural network that gives whatever we need and has one fixed basically set of parameters. Okay, so that was the idea of amortization. So what we did, we introduced this function f lambda as the encoder. So f lambda as the encoder will have a fixed theta. Just not fixed, that means you still learn it, but one theta for all sorts of data that you are basically receiving. Similar to, so decoder that has phi, just one phi, encoder also will have one theta. So here, to just finalize this, so if we looking at this basically missing pixels part of the image, so basically the overall idea was that, hey, I need to have, for this image, maybe have series of basically theta I that I need to learn. And the idea here will be that instead of doing that, we're going to learn this model Q, Z, F lambda, Xi. That means this, this basically, so remember previously we had Q, Z, theta. So this was Q, Z, theta I basically. So instead of that, that theta I, basically, instead of that theta I, we basically have this model that gives us whatever value that we need. So we don't need to learn one model, what parameters per data point. We just have one fixed neural network that basically does the job for us. So that becomes the amortization part. So that's the last part. So this how the amortization version of the variational encoder looks like. So the Q will have this f lambda xi in it for data points, which is, that means a neural network. So this becomes your encoder. This is your decoder whenever there is a P. This is like a decoder. And this is again your encoder. So this part still means reconstruction accuracy. This is the entropy of that basically proposed distribution. And your goal is that maximize this together. So that's how your elbow will become maximized. You can also write it this way as a basically expectation over this minus that, because that's the same term. So, but how you solve it, initialize this too. So here you see we don't have theta I, we just have one theta technically. You sample a data point, you update, so in amortization version, you update phi and theta at the same time. In the previous version, you loop through theta as much as possible until your theta gets to the point that you cannot update it anymore. Then you go to phi. Here you just do all at the same time. Phi, and because you only have one theta, one basic model for theta, one model for phi, so you just update them in one back propagation. Similar to if you think about how the flow of the data could go. So if you have this, like, I'm just simplifying it. So you do a forward and you do a backward once together. In the other scenario, you basically add something this, you did a forward and then forward. Then you did series of backwards here to be sure that this is optimized. Then you did another forward here. Then you did backward on this one time. And then you went over this series of times. So this, because you wanted to be sure that encoder, because you didn't have one set of parameters, you go over it over and over again. In the decoder, you only had one set of parameters, you just do one updates. In the amortization version, because you have one encoder, one decoder, you just work together, forward, backward process, basically. Okay. Any question on that? All right, so that's it for today. So that's the